Hey everybody, so here is the Polyatomics slideshow, and that is when I sent out that text about how it was just me and the crickets in 221. That was a picture of what it looked like when I was there. All right, so polyatomic ions, that's where we are. And polyatomic ions are basically these large groups, these compounds that have an overall charge, usually negative, as you can see. I put them here in order. These are all negative ones, then some negative twos. There's one negative three and one positive one that we'll be dealing with. So it means that the whole shebang, the whole NO2 has a -1 charge, or the whole N and 3 oxygens have a -1 charge, and the C and the N have a -1 charge. And they have these names. So let's get into some rules here. So the first thing is that the subscript here refers to the atom immediately before the numbers. So here you have 2 referring to the hydrogen, and that means there are 2 hydrogens for every oxygen in water, and you might have learned that already. In acetate, which is C2H3O2 minus, that means there are 2 carbons seen here in the picture, and there are 3 oxygens. There's 3 oxygens here, and 3 hydrogens and 2 oxygens. 2 oxygens there, and the whole thing has a minus charge, which we'll learn later. All right, parentheses. If, however, you put something in parentheses, that'll sort of distribute the subscript. So if you have NH4 2, so 2 NH4 groups, you would put the whole NH4 in parentheses, and that 2 then distributes to both the hydrogens and the nitrogens. So you can see here, here's one NH4 group and nitrogen connected to 4 hydrogens, and here's a second NH4 group. And that's what you're trying to communicate with parentheses and then the subscript. The subscript then would distribute through the parentheses, as opposed to here where it's just talking about the atom right before it. All right, hopefully that makes some sense. So if we have something like potassium phosphate, now you know from your periodic table placement that potassium is a +1 charge. Phosphate, you will know from that list, has a -3 charge. So just like before, like if we had potassium nitride, where nitrogen had a -3 charge, potassium phosphate, where this has a -3 charge, needs to cancel out the charge. The potassium needs to cancel out the -3 from the phosphate. So 1 is not going to be enough, because +1 does not cancel out -3. +2 is still not enough. You need 3 ions, 3 positive charges, so that 3 minus 3 equals 0, so that everything cancels out. And that means you needed 3 potassiums for every phosphate ion. And that's how we would write it. All right, so the same thing goes with ammonium phosphate. Ammonium is this whole group and it has a +1 charge, and phosphate is this whole group and it has a -3 charge. Just like with potassium, it would require 3 of these, 3 times the +1 -3 to equal 0. So we need 3 +1s to cancel out the -3 to get to 0. So +1 +1 +1 is 3, -3 is 0. And so this is the phosphate. You only needed 1 phosphate to go with the 3 ammoniums. And now we need to use parentheses because we want this whole ammonium group to be taken 3 times. So you write that as NH4 with parentheses all around it, 3. So you take the whole thing 3 times and then the PO4. All right, so here are the rules for naming polyatomic ions. The polyatomic ions with their subscript and all, you need to take the whole thing. You don't just take, for example, with the PO4, you don't just take the PO as some people have tried to do, or just the NH. You need NH4 for the ammonium and the PO4 for the phosphate. You're going to use parentheses if you want more than one polyatomic ion. So here are some examples. Potassium carbonate. Do it again, kids. So potassium carbonate. Carbonate, if you look on the list, is CO3 with a -2 charge. -2. And we were talking about how important it is to keep capitals. So this carbon is capitalized. That's a capital O, Because if that were a lowercase o, this would be cobalt, and it's a whole different thing. So every time you have a capital letter, you've moved on to a new element. So even though that doesn't look like a capital, because I'm incapable of writing on my computer, that is a capital O. It's amazing. All right. So carbonate is CO3 minus 2. Potassium, as we just discussed, is K plus 1. So if you have a plus 1 and a minus 2, hopefully it goes to reason that you need 2 potassiums to go with your carbonate. So potassium carbonate would be K2CO3. You need 2 potassiums and just one of the carbonate groups, one CO3 group. That wasn't my worst job. In fact, that could be award-winning. Look at this. I'm going to give myself a medal for that one. All right, so that is my medal. All right, so ammonium sulfate. Ammonium sulfate has ammonium, if you look on the chart, is NH4. Ooh, that's a good one too. Getting better at this, I guess. All right, NH4 with a plus charge. Sulfate, if you look on the list of polyatomic ions, is SO4 minus 2. So if that's SO4 minus 2 and that's NH4 plus, hopefully it stands to reason that you would need 2 of these pluses to counteract that minus 2. So you would need 2 NH4s and H4 taken twice. So NH4, to show that we need it twice, we put it in parentheses. And then I should just give this to people in therapy and see if they can see any weird things in these ink blots, because that's about what that is. All right, so you need 2 of those, and then you need an SO4. All right, maybe it's my problem. It looks like a guy, doesn't it look like a guy? Like this is the back of his head, and that's the front of his head, and he's thinking about NH4, and he has a 2 coming off the back of his neck. Maybe a curl. Maybe someone just cut his hair. So there's his hair, and somebody just cut that off. All right. I'm so bored. All right, so that's where you get those. Oh, look, I didn't even have to read anything. I shouldn't have written a thing. All right, so we won't do those. All right, so here's the summary of polyatomics and binary. You always go in the order from the positive cation to the negative anion. It's always written positive to negative. So metal to non-metal, or in this case, polyatomic cation to anion. You always adjust the ratio of the cation and the anion so the charges are equal to 0. The negative form or anion of an element ends in IDE. So if you pull something off the periodic table like chlorine or iodine or oxygen, and you make it negative, -1 or -2, however it is, you want to make sure when you name that, it ends in IDE. Polyatomic ions, since they are already charged and named as such, you don't need to change their names. So there. All right, so that means here. So fluorine, where am I? Where's my pointer? There I am. All right. So fluorine, chlorine, bromine, iodine. See, these don't end in "ide" until you make them negative. So F minus becomes fluoride, because if it weren't charged, it would be fluorine. Charge is fluoride. Chlorine is no charge. Chlorine -1 is chloride. Oxygen with no charge is oxygen. Oxygen 2-, looks like a pork chop, is oxide. All right. I had baked ziti for dinner, by the way. So not pork chop envy. Very happy with baked ziti. So if you pull a negative thing off the periodic table, you end in "ide." All the metals, regardless, have a plus charge. All right. So then we discussed today that a leading H means something is an acid. When H is acting like a metal, that is to say, forming sort of an ionic compound where H is leaving as H plus and the Cl here is Cl minus, or the SO4 sulfate is SO4 2-. So the H is sort of acting as H plus here, like a metal. That means it's an acid. And that's all you have to recognize, is that when you have a leading H, an H on the front of a formula, that means it's acidic. So there's nitric acid, acetic acid, sulfuric acid. Okay, and then the last thing we talked about is that the roots of carbon chains are very helpful in establishing how many carbons people are trying to talk about. So meth means that there's one carbon. Eth means that there's two carbons. Prop would mean that there are three carbons. And you'll see this a lot if you especially look in newspapers for chemical stuff, or if you look in a textbook when you're in biology or something, you'll see a lot of like propyl something or others, or, you know, it's amazing how often these things come up. All right, so the hard ones are here: methyl, ethyl, propyl, butyl. Those are hard ones. Pent, you should know, has 5 because of the pentagon. Hex, you should know, is 6 because of hexagons. Popular shape. Heptagons are not that popular. Some of you knew that. That's fine. But octopus and, you know, octagons or whatever. Yeah, octagons. That's the thing now, isn't it? Because all the crazy fighting that happens. All right, so these are pretty obvious. This side here are pretty obvious. This side here, probably new to you. So the way to remember that, the mnemonic, is that monkeys eat peeled bananas. So methyl, ethyl, propyl, butyl. 1 carbon, 2 carbons, 3 carbons, 4 carbons. And that ought to get you through there. So there we had the wonderful picture of a baptism of a molecule because it was being named either methyl or ethyl or propyl, butyl, pentyl, hexyl, heptyl, or octyl. All right, so these you need to know, and I think that's it. Thanks for watching, kids. I'm not going to make you do that yet. Maybe another time. Maybe another time. All right, now you just got to deal with me till I find the stop. Here it is. Have a good